Hello, welcome everybody to our perspective seminar this week. We have the pleasure to have Michele Galli, who's going to tell us about consistent truncations and spectroscopy using exceptional field theory.
Thank you very much. So first, I'd like to thank you for the opportunity to come here and visit and speak at the university. And so like Gabriel said, today I'd like to talk about some work that I've been doing the past 3 years during my PhD about consistent truncations and KK spectrometry via exceptional field theory. So everything is based pretty much on these three papers that I worked on with my supervisor Emmanuel Malek and Henning Sandleben, his PhD student Bastien Dobeuf, and Camille Leloy. So just a very brief motivation. So as you all know, string theory requires space-time to be 10-dimensional, and so the typical question that one then asks is, if I want to describe some lower dimensional theory, what should one do with the extra dimensions? And we know that the answer is to curl them into a compact geometry and then ask, how does the geometry of the compactification affect the lower dimensional physics? But so what I would like to focus on today is a slightly different perspective, and it's more this dashed arrow. So saying, suppose you already have a lower dimensional theory, which is typically relatively simple compared to the full 10D string theory, and you know somehow that this comes from a compactification. The question you want to ask is basically, how much information can you extract from some simple lower dimensional toy model about the full 10D physics? And I would like to convince you that the punchline will be that it's actually quite a lot of information, surprising amount. And to do it, I will use the tools of gauge supergravity and the exceptional field theory. So everything will be in the supergravity regime. Okay, so again, the main motivation is that it's very hard to find solutions directly in 10 or 11 dimensions, because the supergravity equations involve several fields of different types, p-form potentials, and a metric, and they all source each other in a very nonlinear way, and so it's hard to solve the equations. So the strategy will always be to work in a lower dimensional model, solve the equations there, and then uplift the results to find solutions in 10D. And everything is motivated by the ADS-CFT correspondence, so to try and understand things about holography, and more recently about non-supersymmetric ADS vacua, and in particular their perturbative stability. The main physical tools and the technology that we'll use are consistent truncations, which are especially useful to find solutions, and the newer tool of Kaluza-Klein spectrometry, which is what allows you to really extract more information, especially in the context of holography and stability. So I'll start by just saying, giving an introduction about consistent truncations, what they are, why they're useful, and how they're constructed in this framework. And then I'll give 2 examples where we applied all this technology to learn new things and obtain some nice results. Okay. Oops. Sorry. Okay. Okay. So first, consistent truncations. So I'll start by the definition. A consistent truncation is whenever one has some physical theory which involves a set of fields, and what you want to do is truncate some of them, so discard them, set them to 0, and this process of truncating the fields is called consistent whenever you have the property that any solution of the truncated theory, which has fewer fields, is always guaranteed to also be a solution of the full system that you started from. So a nice example of this is one you probably all know, is if you want to consider gravity in d dimensions on a d-dimensional manifold where one dimension is compactified on a circle, you can write an ansatz for the metric like that. And I mean, the fact that this is a truncation is simply comes from the fact that any a general metric will not look like this. This only describes the dynamics of a d-1 metric, a d-1 scalar, and a d-1 potential. And so this is, so in this sense, this is a truncation. Then you can ask if it's consistent, and the answer is it is. You can check. You can check that by plugging it explicitly into the Einstein equations and seeing that the system of equations, after you plug this into the Einstein equations, the system of equations that you get in terms of these lower dimensional fields is always guaranteed, whenever you solve them, is always guaranteed to uplift also to a solution of the full gravity theory in the dimensions. And then an interesting question that you might ask, for example, in terms of, for the historical point of view, this program was created to try and unify gravity and electromagnetism. So an interesting question that you might ask is it consistent to further truncate the scalar away? So you can be left only with gravity and electromagnetism. And the answer is that it is not consistent, because if you look at the circle-circle direction, this ZZ direction of the Einstein equations, you find an equation of this type. And in particular, you see that the scalar field is sourced by the field strength of A. So setting phi to 0, just getting rid of it, is not consistent. Okay, so this was a relatively simple example, because here consistency could just be checked by explicitly plugging the ansatz into the equations of motion. But in general, this is very hard to do, especially for supergravity, 10-11 dimensional supergravity. And so in order to construct consistent truncations, the strategy will be to use a symmetry argument, which roughly speaking goes into two steps. There will always be a Lie group acting on the fields, and the prescription will be to only keep in the truncation fields that are invariant under the action of G. And schematically speaking, this 1 times 1 = 1 equation says that invariants, so singlets, cannot source non-invariants. So you will never have a situation in the equations of motion where you have a bunch of fields that you're keeping, which are invariant under the action, sourcing something that you've thrown away, which is not invariant, because you cannot have that by group theory. And so you avoid precisely the situation like with the scalar in the previous example. Then the second step is a slightly more technical, more complicated condition. Since you will want to do dimensional reduction, the equations of motion of the full theory will involve derivatives along the internal dimensions. And so to ensure that the dependence on the internal space factorizes out of the equations of motion, you would like you will require that the derivatives of these invariants that you want to keep can also be expanded in terms of the same invariants. And all of this can be formalized using the mathematical language of G structures.
Are those consistent conditions for consistent truncation?
Sorry,
If you impose those conditions,
Yeah.
are you guaranteed that this reduction is consistent?
Yes, exactly. Yes. So it's whenever you have these two things formalized in terms of G structures that I'll discuss now, it tells you that the truncation is then guaranteed to be consistent. Yes.
You should say, as in your previous example, that you should keep only invariants, but every invariant.
All invariants. Yes, this is a good point. So you should keep all the singlets. This is a key point. You should, because again, you don't want, if you got rid of some singlets, they could be sourced by something that that is still a singlet that you've kept. So this is a good point. Yes, you have to keep all this, only singlets and all the singlets. Okay. Any more questions?
But even if you do that, would it be possible that maybe there are solutions where some of the singlets are absent?
So you mean solutions where some of them are zero?
Yeah.
Yes. In fact, this the truncation step says doesn't tell you anything about solutions.
What you want is necessary condition, but you don't have to.
Yes.
There could be some model where some of the singlets are simply not there.
For solutions, yes, sure. So you can have solutions where some of them are set to zero, but the output, if you want, of the truncation is a theory, is not a solution.
Mm-hmm.
So then you can solve there, but so of course then when you solve, a lot of things will be set to zero. But this is the output here is really like a theory, not a solution.
Let's talk about it, but in terms of there is a systematic way of getting answers.
So yes, exactly. So this is exactly. So this is indeed the whole point in a way that the systematic thing is that you can find solutions essentially by varying a potential because you're in lower dimensions, by finding the extreme of a potential, and then the systematic step is the uplift procedure. So you can read off what the solution looks like in 10D from something that you've done in a lower dimensional setting, if you want. Yes. And actually, you can do also more systematic things. So, for example, you can do some kind of classifications, for example, by looking at the G structures that can appear, etc. Yeah. But this is a bit beyond what I'm going to talk about. Okay, so now I'll just give it some. Okay, again, here in this, I'll talk a bit about G structures and these two conditions, how they're formalized, but I'll be a bit schematic because I will not need the full power of the proper formal definitions, but all these things have proper mathematical definitions as well. Here I just give some intuitive definitions, if you want to call them that. So a G structure in this context will always be when you have some manifold that admits some tensors defined on it, and these tensors obey some algebraic relations that define them to be singlets under the action of a group, invariants of a group, and that group will be the G of the G structure. An example that everybody will be familiar with is if you have a non-degenerate 2 form on some manifold, this defines a symplectic structure on it because the 2 form is precisely the tensor stabilized by the symplectic group. And 2 important points. One is that defining G structures in general is a topological matter. It's not just an algebraic thing, so there are abstractions to defining them. It's non-trivial. And then the second thing, I can make the kind of consistent truncation ansatz more precise. What one will always do is, given some field in the theory, which in general depends on both the external x and internal y coordinates, it will always be factorized in this form, where all the dependence on the internal space is encoded in these singlets under the G structure that define the G structure. Now, regarding the second condition. So, like I said earlier, you would like that the derivatives of these singlets can be expanded in terms of singlets. And this is formalized by putting a condition on the intrinsic torsion of the G structure. So you want to demand that the intrinsic torsion of this G structure is constant and singlet. So the intrinsic torsion, again, I only give a schematic definition, is not really, is a tensor. Which is
constant and singlet?
Constant and singlet, yes.
Why constant?
Constant because essentially, so this intrinsic torsion is essentially the components in the expansion of these derivatives. So if you take d of 1 is like a tensor times 1, and you'd want these components not to depend on the coordinates again. They have to be constant. So you don't want functions there of the internal coordinates. Again, because essentially you don't want the internal coordinates to appear in the equations of motion of the lower dimensional theory.
Okay.
They should factorize. Yeah. And so this intrinsic torsion tensor, okay, it has its own specific definition, but in practice, it's always given by derivatives of these tensors. So in this context, the derivatives are external derivatives, Lie derivatives, and various combinations of them. So for example, in the case of the symplectic structure, the intrinsic torsion is simply the external derivative of the 2 form. And again, demanding now that this intrinsic torsion is constant and singlet is in general highly did you have a question? Oh, okay. Is in general highly non-trivial. And for example, in particular, in the case of the symplectic structure, the only way that this can be a singlet is if it vanishes, because the 3-form representation, totally antisymmetric, doesn't have singlets under the symplectic group. And so this can only be constant and singlet in this case if it's just 0. So now I'll give another example, and in practice, this will be the only example to keep in mind because the only one that I will really use for the physics. Suppose that you have some Lie group G, and you know that you can construct left invariant vector fields on it, and that these left invariant vector fields make up a frame for the tangent bundle of G. And so the frame defines an identity structure on G. So the group is now the identity, the trivial group. And then you also know that they have this nice property that they close into an algebra under the Lie derivative, which is isomorphic to the Lie algebra of the Lie group. And then you could ask what is the intrinsic torsion of this G structure, and it turns out that it's exactly the structure constants. So it's exactly the coefficients that appear in that expansion. And so here the intrinsic torsion, it's clear it's always going to be a singlet. This is trivial because the group is trivial. But the fact that it's constant is highly non-trivial, and it really relies on the fact that you're on a Lie group and that you're working with left invariant vector fields. And so this is actually quite an important example because the generalization of this is what I will use for everything in the talk. Okay, so this can be used already to construct a consistent truncation of gravity on a Lie group. So this is a generalization of the first example of the Kaluza-Klein gravity, where the circle is now replaced with a general Lie group. And again, here, for example, you will expand everything in terms of these left invariant objects. So here, the internal part of the metric will look like this matrix Hij, which contains all the lower dimensional scalars. And all the dependence on the Lie group is now again factorized into these left invariant one forms. This is called in general Shirk-Schwarz reduction. So like I said, this type of consistent truncation plays a special role in exceptional field theory because the generalization of this idea will give consistent truncations that preserve maximal supersymmetry. And then maybe a more general point to keep in mind is that demanding that some lower dimensional theory arises from a consistent truncation with an identity structure very heavily constrains what kind of internal geometry you can have. Oops, sorry, I skipped the slide. So now I'd like to motivate exceptional field theory with this example. So suppose you are in D+2 dimensions and you have a theory which contains a metric, a scalar, and a one-form potential. Then it turns out that you can do a consistent truncation on the two-sphere, which takes you to a D-dimensional theory, which contains, again, gravity, some one-form potentials in the adjoint of SU2, and then scalars again. And in order to do this consistent truncation, what you need to do is essentially make up an ansatz for the fields, plug it explicitly into the equations of motion, and prove the consistency directly from the equations of motion. And this is, in fact, quite a complicated procedure, and it only works in particular, for example, if you tune the coupling of the scalar to a specific number with the electromagnetic field. And in particular, you cannot see an explicit symmetry that guarantees the consistency of this truncation from this. But in fact, there is a symmetry principle behind this. But in order to see it, what you need to do is realize that, in fact, these fields are exactly the same ones that you obtain from the S1 reduction that I described at the beginning. And so what you can do is you can work backwards, take these fields, reorganize them back into a metric in D+3 dimensions. And then you find that, in fact, the lower dimensional theory that you obtain from the truncation is the same one that you would obtain by doing a reduction on a group, which is exactly the Shirk-Schwarz reduction that I described in the previous slide. Here, the group is the three-sphere, which is SU2. So in fact, the punchline of this is that there is a symmetry principle behind this consistent truncation, but you cannot see it unless you reorganize all these different fields into some larger objects on some larger geometrical space where the G structure, this identity structure, lives naturally. And this is what exceptional field theory wants to do, what it does.
It cannot be lifted to one higher dimension. Are you saying is there will be no consistent S2 reductions at all?
So so you're saying, what if you have some consistent truncation that doesn't come from this?
Yes.
Yeah.
Is that possible?
Exactly. So it's possible. So because there is no theorem that tells you,
In other words, it's an example, but it does not exhaust possible S2 compactification.
Well, so I think it's fair to say that all consistent truncations arise in one way or another like this. They all come from a G structure. So all examples that are known can be constructed from this. But yes, there is no theorem that tells you that there isn't one.
I guess my question would have to involve, you're right, it would have to involve more fields for me to even imagine such a scenario, right? Because if you only have a scalar and vector field, probably you can prove that this is the only way.
That this is the only, actually, I'm not aware. I don't know if there is if you can prove that from a system of this type, the truncation will always come from a G structure. So I don't think there is actually a theorem, but what there certainly is basically all evidence. So every example comes from this. So it's, yeah. So it's, yeah. Okay, so any other questions?
Suppose I consider S4.
Yes.
I cannot lift it to a group manifold. What will I do then?
Okay, that's a good point. So then that's precisely what exceptional field theory does. So S4 is not a group manifold, but in a sense, you could call it a generalized group manifold. So it will have an identity structure with a constant singlet intrinsic torsion, but it will not be an identity structure on the tangent bundle, but it will be on a larger vector bundle. And this is the one that guarantees the consistency of truncations of type 2 supergravity, basically, and 11D supergravity. And this is exactly what XFT does, precisely. So exactly, so basically, this is it. So what XFT does is it will reorganize the fields into some larger geometrical objects, which is naturally where the identity structures, well, not necessarily identity, but the G structures behind these truncations are defined. And it will work in particular for, say, S4. Okay, so now I'd like to talk a bit about how this enhancement goes. So on the left, there is this example with the two-sphere, and on the right, I have, okay, here I've written down 11D supergravity in a split where you have a d-dimensional compactification and a 11 minus d-dimensional external space. And I just want to show you, the goal of this is to show you how these larger geometrical objects arise naturally. So in the case of the two-sphere, you have these fields, the metric, the gauge potential, and the scalar, which are naturally on the internal space. They're naturally GL2 objects. When you reorganize them into a metric, they become a single GL3 object. So there's this enhancement from GL2 to GL3. Similarly, these are the gauge, the infinitesimal parameters for gauge transformations of these fields. They get combined into a single vector field in 3 dimensions, in a higher dimension. And similarly, the differential operators that define the gauge algebra, they also get combined into a single larger differential operator. And then finally, also the internal, the external scalars parameterize a matrix. They form a matrix which parameterizes an element of this coset space GL3 divided by O3. And analogs of these statements will be true for 11D supergravity. So the enhancement will be from GLD. So these objects on the internal space are naturally GLD tensors. This will enhance to some EDD tensors, where EDD is the exceptional group. Similarly, the gauge transformations will be combined into some objects which we call generalized vector fields. And these generalized vector fields are sections of a vector bundle E, a larger vector bundle E. And then finally, again, the gauge transformations, the algebra, the differential operators that define the algebra of gauge transformations will be combined into a single differential operator on E, which we call generalized Lie derivative. And finally, again, all the external space scalars are combined into a matrix which parameterizes an element of this coset space EDD divided by its maximal compact subgroup HT. So then the task is to try and understand how this EDD appears. And to see how that goes, the simplest way is to do some kind of counting argument where you count what kind of fields you can get in lower dimensions, and you find that they are naturally organized into EDD representations. So again, here I have the 2-sphere and the 3-sphere from the example. There you can see it, for example, if you count the vectors, the one-form potentials, you see that you get 2 from the metric and 1 just from the gauge potential itself. So you get 3 in total. And indeed, if you look at the representation theory, the 3-dimensional representation of GL3 decomposes as 2 plus 1, which matches that counting. And this story of the scalars I already told you. So you have the metric is 3 degrees of freedom, the vector is 2, and the scalar is 1, and this matches exactly the dimensions of that coset space. Now here I've done again 11-dimensional supergravity to see the EDD. This 11-dimensional supergravity, and you write it in a 5. This example writes it in a 5 plus 6 split. And so what you should see here is the group E66 arising somehow when you do a counting of the various fields. So starting from the one-form potential, you see that you get 6 of them from the metric, another 6 of them from the 6-form, and 15 from the 3-form. This adds up to 27. And in particular, if you know some group theory, you see that of these kinds of groups, you see that the 27-dimensional representation of E66 breaks exactly according to that pattern. With the under SL6, it breaks as 15 plus 2 copies of the 6. So this matches. And then similarly, if you count the scalars, the external space scalars, so the internal degrees of freedom, you find 21 from the metric, 20 from the 3-form, and just 1 from the 6-form. And this gives you 42 of them, and this matches exactly the dimensions of this coset space. So this is roughly the counting that shows you how this E66 naturally appears when you write supergravity in this split.
Toroidal compactification, that's still linear and linear.
Yes.
So how, because things about so much.
Yes, I understand.
Here in general.
Yes. So it's
Of course, counting is not enough, right? I mean,
no,
there's more to that.
Yes, of course. There's a lot of field redefinitions, etc. This
Circles are needed.
And indeed, I mean, this, like you say, somehow reminds of this toroidal compactification of the U-duality, but really here there's no compactification yet because this is just a rewriting. So it's really just
Wait.
Yeah.
Toroidal is all flat. It's the same number.
This counting is exactly the same. I agree with Miriam. Same as toroidal.
It's exactly the same.
Counting.
It's exactly the same kind of counting, and it's in a way, I guess you could say that it's a generalization because in a way here it's the same, but here there's no torus, and indeed you will never compactify on a torus.
So how do you prove such a symmetry actually?
I know, but this you can prove explicitly in the sense that you can do the field. I mean, here I just did counting, like you say, but if you do it properly with all the the appropriate field redefinitions, introducing all the duals of the fields, etc., you can really just rewrite the action of 11D supergravity in a E66 covariant way, and see that it reduces to the action of 11D supergravity, for example. So it's the same theory, rewritten in this way. So this is the proof, if you want. You're skeptical?
Like extra dimensions, right? But counting them really like years flat. I don't know.
I see what you mean, but also you have to check.
Rewrite, regrouping.
Yes.
I think the days of Kramer and Julia are long gone. The original work where they showed, E7 symmetry, for example, if you go to 4-dimension,
Yes.
it's an incredible calculation, a nightmare calculation.
Yes.
But nowadays, we don't do this anymore, right? We assume that this is the symmetry and we build from the beginning. We build the exception field theory in which the symmetries are by definition are there.
Yes.
So we no longer are in the business of reduce, combine, redefine.
yeah.
We don't do that anymore.
No, indeed.
Very
Indeed.
hard.
Not relevant. People did in the original papers on exceptional field theory, you needed to do the stat check to the actions of type 2D and 11D. In the entire theory, the entire 10-dimensional and 11-dimensional dynamics are recovered in this splitting was on that is half of the paper.
So indeed, I mean, the action reduces
But
the
the
XF.
crucial first half assumes the symmetry and we build up cleverly.
Definitely, that is the motivation. You want to start from assuming that you have that group somewhere.
Nice.
Okay, please go ahead.
Yeah. Okay. So then, okay. So given this, the strategy is just the final kind of strategy will always be to find in order to construct these consistent truncations will be to find a compactification which admits a G structure on this vector bundle E, and then impose that the intrinsic torsion of this G structure should be constant and singlet. And this is guaranteed to give you a consistent truncation on that space. And in particular, for these examples that I'll discuss, the only relevant case will be the identity structure, and this will give consistent truncations with maximal supersymmetry. And so to go into slightly more detail for this identity structure, all these conditions will reduce to the intrinsic torsion conditions will just be imposing that the algebra under the generalized Lie derivative of this frame that defines the identity structure should have as structure constants these objects that are actually constants. So the only thing that you'll have to check is that these coefficients are actually constants, and so this will give a consistent truncation that preserves maximal supersymmetry. And so now going back, for example, to what you mentioned about the spheres, this has been shown that the N sphere in general admits this generalized identity structure, and this has been used to construct several to prove the consistency of several truncations. Most remarkably, this one was proven using these methods. So spheres, in a way, you can view them as generalized group manifolds. So
That was the factor B, not
yes.
your example was.
Mine was 11D, yes, but basically exactly the same kind of thing goes for type 2A and type 2B. I did 11D because it's shorter, basically. It's easier to see it. Okay, so are there any questions? Okay, so now I'll talk about how we use these methods to construct a consistent truncation of type 2B supergravity on S3 times S3 times S1. And then we used it to study some interesting solutions. Okay, so last year we set up the technology to construct consistent truncations to 3 dimensions using exceptional field theory. And in particular, we were hit with some unfortunate facts. So the first is that okay, so there's no maximal consistent truncation on the 8th sphere. So the next best thing was to construct consistent truncations on the 7th sphere, and we did. We found the consistent truncations of both type 2A and type 2B on the 7th sphere to 3 dimensions, but these had no vacuum. So none of them were terribly interesting. But there are some very interesting solutions with an ADS3 factor, which one could hope to study using these methods. And
Like no vacuum, they don't have any.
yes, exactly. So
Actually, they have the-
okay, this we didn't really study. We just found runaway potentials. So yeah, it didn't seem yeah. So an example of a vacuum that we could hope to, that is very interesting in itself, and we could hope to study using these methods, is this ADS3 times S3 times S3 times S1. It's very interesting for its own reasons. So, for example, one can write a world sheet theory for strings propagating on this background. It's interesting for integrability and several things. And so we thought it would be interesting to understand if we can find the formations of the solution, and maybe say something about the moduli space, and see if we can break supersymmetry in some interesting way, or find some non-supersymmetric solutions, etc. Yeah.
No maximal S8 indication. Is there, for example, an ADS3 times S8 solution?
Good point. Actually, so I looked a bit in the literature, and I never found anything with S8, but I don't know. I'm not aware. I haven't found anything. Nothing explicit. I mean, often you find solutions which are like a S7 fibered over an interval. So this smells a bit like S8. But from what I've seen, typically these intervals are never compact. So so I would say I'm not aware of any. I don't know if anybody is, but I'm not aware of any. Yeah. So okay, so going back to S3 times S3 times S1, the ingredients, the steps that I will use to study all these questions will be first a consistent truncation. The consistent truncation, as advertised, will give you some lower dimensional theory that you can work with. It's relatively simple. And then exceptional field theory allows you to uplift all these results to 10 dimensions and study the 10D physics. So I'll start by discussing the consistent truncation. So this goes in 3 steps. So we want to construct a consistent truncation on a product of spheres. So first we use a result, which is a generalization of the identity products on identity structures on spheres, which is that in the context of 4D consistent truncations, one can show that products of spheres are also generalized parallelizable. So you can they have a generalized identity structure with constant singlet intrinsic torsion. And so what we want to do is start from type 2B, do a compactification to 4 dimensions on S3 times S3. In practice, this amounts to taking an element of the group SL4 squared and embedding it in E77. And then to go to 3 dimensions, you do a further circle reduction from 4D and end up with this 3 manifold with times S3 times S3 times S1. And the second step again amounts to just an embedding of the E77 element that you had there into the group E88. So this is just a chain of embeddings. But this doesn't quite work, and you can see that it doesn't work if you look at the fluxes. So if you look at the solution, this ADS3 times S3 times S3 times S1 solution, you see that it has that red term, which is it's a 3-form flux with all legs on the ADS, on the external space. So its dual will be a 7-form with all its legs on the compactification. And so this kind of 7-form flux is not captured by the 4D truncation that you've done. And so this has to be turned on in the consistent truncation by hand. And there is a nice way of doing that in exceptional field theory. So, and this is to twist the identity structure. So to twist the frame, the identity structure. So what do you twist it by? So intuitively, the 7-form flux has a 6-form potential with, again, all its legs on the compactification. And like I said, initially, all these fields with their legs on the internal space, they're all sitting inside of that coset, EDD divided by its maximal compact subgroup. So you can see that these kind of fields, they will live in the algebra of the group. So what you do is you look for an element in the algebra of the group that corresponds to the 6th form, you exponentiate it, and then you twist the group element. This is still a frame, but the question is what happens to the intrinsic torsion. And whenever you do a twist of this type, the generalized Lie derivative, the algebra of the generalized Lie derivative gets twisted in this nice way. This first term here contains the a constant x, which is exactly the one associated to these untwisted guys here, multiplied now by the twisted ones. And the second term, so this is constant. The second term is the interesting one. Here you see there's this H tensor. This tensor is essentially just the 7-form flux embedded in a funky way into E8. And this is acted on by the untwisted frame. And remember that the untwisted frame is an element of this SL4 squared. So in order to demand for this thing to be a constant times the twisted U, you have to ask that that the action of this SL4 squared element stabilizes H. So it boils down to demanding that the C6 that you found in the algebra is a singlet under the group SL4 squared. And in particular, it is. So we can see that you can find a generator, so an element of the algebra, which corresponds to the 6th form and is singlet under the group SL4 squared. And in fact, this combination turns out to be a constant times the twisted U's. And so you have a consistent truncation. And in particular, if you check at the point where the spheres are round, you find exactly the correct vacuum. So this is telling you that you are in the right consistent truncation. So now, like I said, the output of the consistent truncation is a 3D theory. And the nice thing is that this goes back to your question. The 3D theory has a potential, scalar potential, which looks like this. The details are not so important. The X is essentially this X from the previous slide. Eta is just an E8 tensor. And all the scalars in the 3D theory are contained in that matrix M. So what you need to do is vary this potential. And to find deformations, you can deform M and check that you're always at a critical point of the potential, so that the variation of the potential is still 0. And this gives you a systematic way to try and look for deformations of the vacuum.
So the parent theory here is 11 dimensions?
No, this is type 2B.
Oh, sorry, type 2B.
Yes.
10 dimensions. Now, in type 2B string theory, there is a notion of string tension expansion of the effective action, right?
Okay.
I suppose. Alpha prime expansion.
Yes.
Right?
Yes.
What happens to that alpha prime, that notion in this exception from theory?
Okay, so
lower dimension, what's the meaning of alpha prime?
So this is an interesting question. So I think, so this is all supergravity. So, and in particular here, you're not working with an alpha prime, the corrected theory. So this is sending alpha prime to 0.
So lowers the derivatives.
Yes, exactly. So this doesn't contain the alpha prime corrections. It's really a supergravity calculation.
If I were to consider for derivative extension of this result,
yeah,
then do you have an idea about how that would
about how that goes?
Yes.
So direct.
For example, can I have a higher order terms in a potential? Can this potential develop correction?
It would be interesting to see. So presumably, probably yes. I mean, maybe something
Not
would
been
change.
studied much, I guess.
No, and in particular, I think alpha prime corrections, you can embed alpha prime corrections in this kind of framework, but not for type 2. You can do it for heterotic supergravity.
Okay.
And in this ODD formalism.
Mm-hmm.
But for example, even in that case, I don't think consistent truncations have been studied. So you cannot really, I think, yet see that, if you take the alpha prime corrected theory, say of heterotic supergravity, you can apply all this procedure and cook up a consistent truncation and then see what happens to the vacua.
Not under control.
Not yet, yes,
Okay,
exactly.
thank you.
So we are working on these kind of things as well.
Thank you.
Your previous slide,
Yes.
the deformation it looks a lot like one does in type 2A in order to turn on commands max. Did you also try that?
But this is like what you're saying is typically like a deformation of the generalized Lie derivative, right? But here, I don't think you want to deform the generalized Lie derivative because you want to stay in type 2B.
No, but this is precisely what I mean. So if in your equation, so to say, move the second term in the right hand side to the other side, you can think of that as a deformation of the Lie derivative.
Of the Lie derivative, I see what you mean. Oh, I see what you mean. So you're saying, could you just deform the generalized Lie derivative directly?
So that to turn on all the things that you're interested in, some Romance mass in order to do the theory.
I think in a way you could do it. So in particular, I think you can. So you could start directly from this, yes, but it would still be type 2b.
No, definitely. You need to turn another of the fluxes that you have at hand. And the question is whether you can turn both of them at the same time.
Which other flux?
So the one corresponding to the Romance mass in the, so you would need to break under a different perspective.
I see.
In order to see what is the, well, we can talk about it.
I see. The one thing I can say for sure is that I think so. This SL4 squared only had one singlet when you broke. So I don't know if there are many options, but well, maybe. I'm not sure actually. I'm not sure. You're asking basically if you could turn on other fluxes like this. So I'm not 100% sure. Yeah, I'm not 100% sure. I seem to remember not to that you can't, but I'm not 100% sure from group theory basically by looking at the singlets under this. But yeah, like you say, maybe we can discuss also later. Okay, so we did it. So we tried to deform these scalars and see if we could find some deformations of the solution. And in fact, we found a lot. And so prepare. I will show the nastiest one that we found. So this is a metric on S3 times S3 times S1, ADS3 times S3 times S3 times S1, which is a solution of type 2b for every value of these 7 parameters. So it's a 7-parameter family of ADS3 vacua, which in general break all supersymmetry. So this is not terribly interesting, of course, but this is just to show that basically the power of this formalism is exactly the fact that it's quite systematic. So you can do a reasonably simple thing in 3D, and then the thing that it buys you is to extract some very non-trivial results in 10 dimensions using this nice geometry and this in the Lie groups. So for example, we could find this deformation.
This 4,4?
This is just 0,0 in general.
Oh.
Yeah, because it's a mess. There's a big mess, yes. So the vacuum, when the spheres are round, it is 4,4. Mm-hmm. But this deformation is in general breaks everything. Yeah. So now I'd like to move on to a more reasonable deformation that we found. It can actually be studied a bit. And this is a nice 10D interpretation. Basically, these phi's are angles that parameterize the 3 spheres, and they get shifted by a coefficient times the circle direction. So whenever you have a field, you always replace these angles by themselves plus a shift, and this is the deformation. And interestingly, again, in general, these are 4-parameter deformation, and this breaks all supersymmetry for generic values of the chi's. But there are some interesting identifications that you can make. And if you make some of these identifications, there are some enhancements of supersymmetry to n equals 2, 4, or 6, for example. And the thing to see is that, in particular, these non-supersymmetric solutions, because of these identifications, are continuously connected to some family of SUSY vacua. And so it's natural to ask, can we study this moduli space of SUSY and non-SUSY vacua? Can we understand something about it? And what about the stability of these non-supersymmetric solutions given this limit? Yeah.
The alpha parameter is the length of the set cycle?
Sorry, the alpha is essentially the ratio of the radii of the 2 spheres. This is fixed by the vacuum, and the length of ADS is fixed by the vacuum. It's the chi that is the parameter. Okay, and so now I'd just like to say quickly a few things about the moduli space. And in order to study the moduli space, you really need the full Kaluza-Klein spectrum of fluctuations. So why the full Kaluza-Klein spectrum? I mean, in a way, you can say you've worked out everything in 3D. The solution comes from a 3D solution. So why do you need the full spectrum and not just the 3D spectrum? And this is very simple to see what goes wrong. So imagine you have some simple toy model, a system which has 2 scalar fields. with this potential. So there's a consistent truncation here because there's a Z2 symmetry. So the Z2 symmetry of this is when you leave phi alone and you send psi to minus psi. So the prescription is to keep singlets, so you can throw away psi, and this is consistent. And in particular, you find a vacuum at phi is equal to 0. You can compute the fluctuations along this phi direction and compute their mass, and you find that it's positive. So everything looks okay in the truncated vacuum, if you want. But once you go to the full theory, you can actually compute again fluctuations along the psi direction and find that there the mass squared is negative. And so you have an instability. So this is the picture. In a way, if you are in the truncated theory, it looks like you're at a minimum, but once you go to the full theory, you find that in fact you're not. And so this, sorry?
Not consistent.
This is a consistent truncation because, well, I mean, this is just a toy example, so it really doesn't mean much. But the point really is that, I mean, it's a consistent truncation, okay, but the consistency is just a statement about solutions, uplifting solutions. And this is a consistent truncation. But then the question is whether, you know, like I was saying, I mean, here, the story of the masses, in a way, doesn't care about the lower dimensional theory. It cares about the full solution. In this, for example, in this case. Yeah, this is a toy example, but the same thing can happen in supergravity. I think so, yes. So, so in fact, I don't know if there are many examples of solutions that are stable in lower dimensions, but unstable in higher dimensions, non-supersymmetric, because most of them are already actually unstable in lower dimensions. I don't know, are there examples?
So the most famous one is the so-called point of Nicolai.
Okay.
But
And this is stable in 4D?
so that is stable in the 4D
Yeah.
consistent truncation, or like in the with the Nicolai field. And if you put it in 11D and you compute all possible situations, you see that some of the KK modes are in fact violating the DF bound. Not only, I mean, those modes are higher up in the tower.
Yeah. So this is basically exactly that kind of situation. So, okay, so you have to compute this KK spectrum. And this is, again, in general, very hard for type 2 supergravity or 11D supergravity, again, because you have fields of all different kinds and they all source each other. So it's, in general, very difficult to diagonalize the mass operators. And what exceptional field theory does is basically it allows you to always compute the full KK spectrum of fluctuations around any background on a which admits a generalized identity structure. So basically, just very briefly, the way it does it is whenever you, so what's the simplification? In practice, the simplification is that if you have some background field and you do a perturbation by some fluctuations, here you see that you're expanding it in terms of, you're factoring all the tensor dependence of these fluctuations into the frame that defines this identity structure. So in practice, what you do is you expand the fluctuations in terms of just scalar harmonics on the background. You don't need to involve these tensor harmonics anymore. And so there is no mixing of these different degrees of freedom. And this is the big simplification that allows you to compute the full KK spectrum with these methods. Now this sentence in red, this is a slightly technical point, but until recently, this could only be done if the backgrounds fit inside the maximally supersymmetric truncation. So this is no longer the case. We still need the background to admit a generalized identity structure, but it doesn't have to have this constant intrinsic torsion in a sense. So it doesn't have to fit into a maximally supersymmetric truncation anymore. As long as topologically the background is parallelizable, you can use the spectrometry. So this is not so important for this example, but it will be crucial for the next. Okay, and so I don't have so much time, but maybe be quick. So finally, we apply the technology to this deformation, and we find that the full family, including the non-supersymmetric points, is per. Oh, what happened? Okay, it's back. Good. That the full family, including the non-supersymmetric points, is perturbatively stable within type 2b. And we also find by looking at the KK spectrum that it is periodic. So it's quite interesting because if you look at the spectrum of the 3D fields, there's no specific patterns. It's just kind of some random lines. But if you include the higher modes, so the spectrum in the full type 2b, you find that some higher KK modes become light and they map into each other. And so then the spectrum becomes periodic under these integer shifts of the chi. And so this is evidence that the moduli space is compact. So we can see that the moduli space is compact by looking at the spectrum, and we can show that these non-supersymmetric solutions are perturbatively stable. Okay, sorry. Okay, so this is just a review of what I've done, but I'll skip it because I don't have much time. And I'll move on to the next example. Are there any questions? No. Okay. So now I'll talk about a domain wall solution that we found in 11D supergravity compactified on the 7th sphere. Okay, so can I go like 5-10 minutes over? Yeah, thanks. So so the setup is the following. So you have the ADS CFT, and this relates strings on ADS times a compact space to a CFT on the boundary of ADS. Then the holographic renormalization gives you a dictionary gives you basically a duality, a dictionary that relates domain wall solutions between ADS times different compactifications. So domain wall solution interpolating between different ADS vacua relates that to an RG flow between the CFTs dual to these two vacua. And the idea for us was to study a domain wall solution in 11D using exceptional field theory, and then use it to extract results about the RG flow. So the specific case that we're studying are two very old, well-known vacua of 11D supergravity. So one is the ADS4 times the squashed 7 sphere, which is a n=1 solution. And the other is the famous n=8 solution, which is ADS4 times the rounded 7. And the strategy to use XFT to study all of this will be to work in a consistent truncation, which preserves n=1 SUSY, and only involves 2 scalar fields. So we'll work in 4D with just 2 scalar fields to find the solution. A crucial thing is that this n=1 truncation that I'll work with is not a subtruncation of the n=8 famous n=8 truncation that contains this round vacuum. It's a different one. Okay, so by going to 4 dimensions, one can solve the Einstein equations using this domain wall ansatz for the 2 scalars. And in particular, the flow is non-supersymmetric. And so we had to do it numerically. We found the solution numerically. And we found that by doing an asymptotic expansion near the UV point, so near the squashed sphere solution, we found that the flow is triggered by a relevant operator, which is in particular dual to one of the two scalar fields. And we could use XFT to uplift the solution. Sorry.
When you still have a ground state with n=1 here and another one, you're breaking 1/2 of the supersymmetry. That's the phenomenon for the supergravity.
So why is it not supersymmetric?
It must be some first order equation that you have to still satisfy.
but
You're right.
I think the point is that here you can show that this flow is USP4 times SU2 invariant, and you can show that you cannot solve the supersymmetry equations if the flow is USP4 times SU2 invariant. And in fact, I mean, in 4D, the way you see this, so this is in 11D, but if you want to see why in 4D it's not supersymmetric, this vacuum actually in the 4D truncation, the round one, looks n equals 0. And it's because basically the spinors, the Killing spinors of the round S8 are not kept in the truncation because they're not USP4 times SU2 invariants. And so basically this vacuum, if you look at it in this 4D theory, looks n equals to 0, but it's not n equals to 0. It's the n equal to 8, 1 in 11. Okay, yes, sure. And
V is the squashing mode.
Yes.
You probably want a minus sign on one of it.
It could be, yes, it could, there could be a typo easily, yes. It's probably wrong, yeah. But exactly, U and V are exactly the parameters that regulate how it's squashed, yes. Okay, so this is the profile of the two scalars, numerically how they look in the solution. And oops. And is the flow. So the red point is the squash sphere, and the green point is the round sphere. And so you flow from the squash to the round. Now I will use this red remark that I mentioned earlier. So in particular, this consistent truncation, like I said, is not maximally supersymmetric, but the S7 has this identity structure, and so we can still apply the spectrometry. And we can do it, and in particular, we can work out the quadratic couplings of fluctuations to the background. So these phi's, this is just an example of the scalar sector. So these phi's are fluctuations, and the way we obtain this kind of sort of nice 4D effective action. I mean, it looks like a 4D effective action. Of course, it's not 4-dimensional because these are higher modes. But the way to get this in XFT is to simply take the background that you started from, deform it by including the fluctuations, plugging everything into the exceptional field theory action, and then this basically comes out of it. So it spits out a sort of 4D effective action where you see how the fluctuations couple to the background. And in particular, this gives you, in principle, all the information to go and compute two-point functions along the entire flow. Another interesting feature that you can observe from this is are some symmetries. So for example, this is a potential, and this phi 345 is really like a phi 3 plus phi 4 plus phi 5. And you see that only this combination appears in the entire potential. And so you can deduce that 2 out of these 3 fluctuations are not physical, and they will be Goldstone modes along the entire flow. And this can be done with several other fields. And it's nice because you can see, for example, that some fields, I seem to recall phi 1, for example, drops out of the potential when you go to the UV point. And so you see that this is a Goldstone at the UV point, but then it becomes physical along the flow, and so on. So you can really see all these things manifestly when you have this effective action. It's not really effective, but this kind of thing. And so this is just the recap. Again, we found numerical solution for the flow, and we could do these nice things. But I think the main takeaway point from this is that even when you have some backgrounds that don't fit in a maximally supersymmetric truncation, like this one, and that's very restrictive, we can now use Kaluza-Klein spectrometry anyway to really get some concrete results about the field theory. So about the two-point functions, for example. So this is all I wanted to say. Thank you very much.